And welcome back. As we go ahead and examine another data structure type, this time we're going to go ahead and look at that of the binary search tree. So what is the tree data structure? Well, the tree data structure is just a more complicated data structure that we have that we can compose with links. Moreover, trees are actually a very important, very widely used data structure. And we're going to briefly kind of outline the general techniques used to construct and to manipulate trees. So when we look at binary trees, one of the things you'll look at, you see this picture here, we can see that it is a lot different than what we saw previously with some of our examples with linked lists and hash tables, because you can see how it kind of starts splitting off into branches. In a tree, you can reach any node from the top or the root node by some path that follows these links. And you note there's no cycles in tree. It doesn't necessarily restart over. If you follow the links, you don't go back to the beginning. Instead, you simply just get to an end of that tree. And so if we look at how does this actually look in code? Well, here's a quick example here. And of course, we're just kind of omitting some of the code. But just to give you the structure idea, we can see that we have a public class here. And we have inside of that our constructor, which is creating just our nodes. So we have an int called data. This one has a node called left link, a node called right link. And then, of course, we have a root node. And one of the things you'll notice is that there's, of course, two references. Of course, like we said, we have the left link and a right link in this tree. And we often call this a binary tree because each node has exactly two link instance variables. So every time we construct a new node, you can see, again, we have a left link and a right link. Now, there are other kinds of trees with different numbers of link instance variables. However, the binary tree is the most common one that we're going to work with. Now, in that list, of course, you saw we had a root node. The instance variable named root serves a purpose like that of the instance variable head within a linked list. The node whose reference is the root instance variable is, of course, called the root node. Any node in the tree can be reached from the root node by simply following the links. We just simply trace them back to the top. Below the root, we'll have, of course, what are known as leaf nodes. Now, the term tree, you may think a little bit almost like a misnomer from what we might be used to, because when we visualize this, the root is at the top of the tree, and the branching structure kind of looks like a root branching structure in a tree because it's starting narrow and then branching downward. However, if you really kind of think about it, you could just take that picture, flip it upside down, and it'll look then much more like a tree. So you really effectively, you're starting at a trunk, and then you're making your branches as you're kind of building that out. Now, the nodes at the end of the branches with these link instance variables that are eventually set to null are what's known as leaf nodes. All right, and it's a terminology that may make some sense if we think about how this is inverted of a tree. By analogy to an empty linked list, an empty tree is simply denoted by sending the link variable root equal to null. Now, another thing to understand about trees is that they are recursive by their very nature. It's a recursive structure because think about how we have done recursive functions. All right, each tree, in effect, has two subtrees whose roots are the nodes pointed to by the left link and right link of that root node. So you're always having to kind of trace back. This natural kind of recursive structure also makes trees particularly amenable to recursive algorithms. So if you start using recursive functions and you need, hey, I need a data structure that's going to work very well to it, this is where recursive algorithms would work very well. Now, additionally, trees use different kinds of processing to handle the data. First is the pre-order processing. So let's consider the task to search the tree in such a way that you visit each node and do something with the data, such as just writing out the screen. So it's something very simple. All right. Well, the first thing it's going to do, it's going to first process the data in the root node because it's always going to start at the top. It's then going to process in the left subtree, and then it's going to process in the right subtree. You can obtain several variants on the search process, of course, by varying the order of these three steps. Once, of course, we have that, then we're going to move to what's known as in-order or post-order processing. Well, in-order processing is we say, hey, we're going to start with the left tree, then we're going to do the root, and then we're going to do the right tree. The other variant that we can look at is what's known as post-order processing. We would process the left tree, then the right tree, and then we would look at the root. So again, these are all different processes of how we can handle this data. Now, the binary search tree has certain storage rules here. First off, all the value in the left subtree has to be less than the value of the root node. all the values in the right tree are greater than or equal to the values in the right node. And this rule also applies recursively to each of the subtrees. The base case for the recursion, of course, would be an empty tree, which is always considered to satisfy the rule because, remember, it has to fit in recursively. And of course, we have to have that less than, and then we have the greater than or equal to. So having an empty tree works really well to meet those conditions. Now, when we have our binary search tree storage rule, this, of course, is going back to those binary trees, or specifically binary search trees. If a tree satisfies the binary search tree storage rule, so that 1, 2, 3 we just saw, and we output the values with the in-order processing method, so in other words, it's going to go left, root, and then right, the numbers then will output in the order from smallest to largest. For trees that follow the binary search tree storage rule and that are what's considered to be short and fat trees rather than tall and thin trees, which means we have a, we don't have a long list of nodes that are going straight down. Values in those trees are very quickly retrieved from the tree using a binary search algorithm that's similar to the binary search algorithm that we have previously looked at in programming 2. Now, the topic of searching and maintaining binary storage tree is to realize this efficiency is a large topic that's actually going to go beyond what we're going to discuss here. However, we're going to give an example of the trees that satisfy this binary tree storage rule. So let's go ahead and look at that example of this binary search tree class. This class is called entry, which we looked at a little bit of the sample of that code previously, and it has a definition for a class that's going to satisfy that rule. For simplicity, this tree is going to simply just store integers, but a routine modification can produce a similar tree class that stores objects of any class that implements the comparable interface. Now, note that no matter in which order the integers are inserted into that tree, the output, which uses order traversal, outputs the integers into a sorted order. So, again, going back to that binary search tree storage rule, the left and right subtrees do themselves satisfy the binary search tree storage rule, so it's natural to use recursion to process the entire tree by doing the following. First, we process the left subtree with root node, and we just say a node.leftLink. Then we process the node, a node. And then we process the right subtree with the root node a node.rightLink. Note that we process the root node after the left subtree. So this is, again, in order traversal. This guarantees that the numbers in the tree are outputted in the order from either the smallest to the largest. Now, the method show elements in subtree uses a very straightforward implementation of this technique. Other methods are a bit more subtle in that only one of the two subtrees actually needs to be processed. And if we go ahead and look at is in subtree, this is one of our methods that we have here. We have some pseudocode to kind of process this. This method, of course, simply just returns true or false depending whether or not the parameter item is in the tree with the root node subtree root. To see if the item is in any place in the tree, we simply set tree subroot equal to the root of the entire tree, as we did within the method contains. However, if we want to express our recursive algorithm, we need to allow for the possibility of subtrees other than the entire tree. And of course, here is that pseudocode. If we look at, we have an if statement that first checks to see if it's empty, otherwise we return false. If it contains an item, it's going to return true. If that item is less than the data, we return the result of searching that tree from the left link. And then we have an else statement, which of course effectively is the item has to be greater than the linked data. And then it gives the result of searching the tree with the subtree's right link. So with the algorithm, all right, because remember, we're looking at recursive ones. The reason why the algorithm gives the correct result is that the tree satisfies that binary search tree storage rule. So we know that if the item is less than the subtree data, well, then the item has to be in the left tree, if it is anywhere in that tree. And if item is greater than the subtree root data, well, then it has to be in the right subtree, if it's within that tree at all. Now, the method with the following heading uses techniques very much like those that are in is subtree. Private int tree node insert in subtree, int item, int tree node subtree root. So what is subtree root? Well, subtree root is, of course, something a little bit new here. We want that method insert in subtree to insert a new node with the data item into the tree with the root node subtree root. But in this case, we want to deal with subtree root as a variable and not it only as the value of the variable subtree root. If subtree root contains null, then of course we want to change the value of subtree root to a reference of a node containing item. However, Java parameters cannot change the value of a variable given as an argument. So we have to do something a little different if we want to actually accomplish this. So let's look at how we actually change that value. Well, to change the value of the variable subtree root, we return a reference to what we want the new value to be, and we invoke the method subtree root as follows. Subtree root equals insert in subtree, item, comma, subtree root. That is kind of a great explanation why the method insert in subtree returns a reference to a tree node, but we still kind of need to explain why we know it returns a reference to that desired subtree. So let's look at that method, insert in subtree. This method, what it is doing is searching the tree just as the method is in subtree does, but the big difference here is it does not stop if it finds the item. Instead, it's going to search until it reaches a leaf node, or in others, a node that contains the value of null. This null, of course, is where the item belongs in tree, so it replaces null with a new subtree containing a single node that contains item. Now, you may need to think about the method insert in tree a bit to see that works correctly, and we'll look at this code here in a minute. And give yourself time to study the method and be sure you're convinced that after the addition, like the following, subtree root equals insert in subtree, item, comma, subtree root, that the tree with the root node subtree root still satisfies that binary search tree storage rule. Remember, there's 3 steps that it has to go through in order for it to meet that condition. Now, let's put that aside for a minute and actually look at the efficiency of these binary search trees. When you're searching a tree that is as short as possible, notice all paths from the root to leaf differ by at most 1 node. And the search method is in subtree, and hence also the method contains. This is about as efficient as a binary search on a sorted array. Now, this really shouldn't be too shocking to us because the 2 algorithms are very similar, as we previously mentioned. In big O notation, which of course is the worst case runtime, we're looking at a big O of log n, where n is simply just the number of nodes in the tree. This means that searching a short, fat binary tree is actually very, very efficient. Now, to obtain this efficiency, our tree does not need to be as short as possible, so as long as it comes close to being as short as possible. It's an ideal measure that we want to try and push. Now, as the tree becomes less short and instead becomes tall and thin, the efficiency is going to fall off from that big O of log n that we saw. And in the extreme cases, the efficiency is actually going to end up being the same as if we had searched a linked list with the same number of nodes. Now, maintaining a tree so it remains short and fat as nodes are added to our tree is a topic that's going to be on the scope of what we're going to cover here. Now, we only need to note that if the numbers stored in the tree arrive in a random number, then there's a very high probability that the tree will be short and fat, enough to realize the efficiency that we have discussed previously. And here we are, of course, over in Eclipse. If we look, here is our method, int tree, and we can see how this is set up. Here is our node right here. So we have a private static class tree node, and we can see we have 3 pieces. Here we have our data, we have our left link and our right link. We have our parameterized constructor right here, which is, of course, feeding in those pieces right here. So we're getting in data, a new left link, new right link, and it allows us to set those to those link values here, which is what we want. And once we go ahead and get outside of that kind of link class here, you can see that we are creating our root. We're setting that root to be null because we want that to, effectively, this is going to be our empty tree. And then we, of course, have our add method, which, of course, just allows us to insert that. We have contains, which, of course, it calls the is in subtree. And we have show elements, which is going to show us. So those, of course, are going to fall right down here to these 3 methods. And on these methods, you'll also notice that these methods are private. So these are not methods that you're going to call. So you're not going to have to worry about calling, hey, insert this into subtree, or is it in subtree, or show elements. Instead, you simply just use like add, contains, or show elements. So that is kind of nice here. Once you have this implementation carried in, you don't have to worry about it. And you can see, we have our if here, which of course is checking to see if it's null. We have our else if to see if it's less than, so this is going to handle our left side. And we have our else, which effectively is a greater than or equal to, which handles our right side. And then we go a little further down, and we can of course see that we have our is entry, which of course is, again, very similar to what we have seen. We have our test to see if it's null. We have to see if it is equal to the item. We look to see if it's less than. And of course, this is effectively greater than or equal to. And lastly, show elements in tree is using in order traversal to go ahead and traverse through that list. And you can see how it is doing. It first calls let's see if it's not null, because if it's null, well, it's empty. So we look to see if, hey, we're going to show the left link elements, and because you can see it's effectively calling itself here, this is a recursive algorithm. So this is using recursion to call itself and then simply call that data until it can print it out. Then, of course, it has the right elements here, which are going to then go through that right tree. So again, using recursion here to go ahead and go through each of those items there. And if we look at our demo here, we can see it's, for us as the end programmer, it's actually pretty easy to do. So all we do is we're going to turn in a list of non-negative integers. We're putting negative integer to indicate the end. We're going to add it in by just getting keyboard input, and we're just going to print those in shorted order. So if we go ahead and run this program, let's just go ahead and put some random numbers here and here. So I'm just going to make some nice quick additions, and let's just do -1 because I'm real quick demo here. And you can see it says in sorted order, and we get 1, 2, 4, 5, 7, 9. So again, this is a real quick way for us to show how that program has used. And again, this is really cool because we can bring in recursion to go ahead and do this. However, again, remember this only works really well when our trees are kind of short and fat. So we have our nodes kind of branching outward rather than branching upward.